building them, and you can use them in practice, but they are still limited in size and also in what you can actually do with them because of noise that we will talk about more in a moment. And a lot of projection and people have roadmaps that they say they will be able to do error correction in some form or another in the coming years. So it can vary from next year to like in 3 years, depending on who you ask. But this like near term, let's say mid-term computers will still be limited in size just because the amount of qubits we need to get a large scale fault-tolerant quantum computers is very large. So by 2028, 2029, sorry, a lot of providers have a target of 100 qubits that can run 100 million gates. That's like the sort of ballpark estimate you will see. On different architectures, whether it's like superconducting qubits or neutral atom or trapped ions. But this in itself is still not a like fully fault-tolerant quantum computers, mostly because you would need like millions and millions of qubits for this. And for this, the like range of when we expect like real like practical quantum computers is more like after 2030, after 2040 if you're a bit less pessimistic. I think it depends who you ask too, but yeah, but up to there, and I would even argue at the end of the talk, even in up to like early fault-tolerant part, we will need error mitigation, and that's why we need to be aware of it, and if possible, choose carefully what to run and how to run. So what does error mitigation actually entail? And this is like going a bit once again outside of the pure theory of error mitigation. I would argue that it has like these three steps where you have a circuit, you've done all your like algorithm research, and now you need to run it. So the first thing would be some pre-processing steps, which are, so to speak, not error mitigation yet, but there would be compilation of your secrets, optimization of your secrets. So here you can use a lot of different techniques, like a lot of people using reinforcement learning or like approximate synthesis, or like even just clever logical transformation that you do by hand. Then you will have to choose the hardware, and you will get some hardware-aware like steps. So mostly layout optimization and routing, which like qubit in your secret correspond to which qubit on your device. This is also in general a very hard problem that I will not talk about, but it actually has a lot of impact on the final performance you will get. And then you will have what you will focus here today, which is actual physical noise mitigation and noise suppression. So here's a list of techniques. I think I will probably talk about all of them and maybe some extra more, but there are also some that are not on this list, but that you could use. And finally, and I will also touch on this quickly, once you get results, you can still get classical post-processing technique based on heuristics, like knowledge of what the result you expect, type of things. So these are also very important, and I will, as I mentioned, I have a quick slide on this. So when we talk about error mitigation, this is like a brief outline. This is like not super like sharply defined transition, especially between error suppression and error mitigation. Like the distinction is vague, but I will try to go in order. So we first talk about representing noise in quantum computers, because to find the noise we need to understand it, and then I will describe some of the error suppression and error mitigation techniques that, once again, we use in practice. So I will try to emphasize the ones that are the most, let's say, cited in literature, and then, okay, touch on the post-processing step. So in general, noise is actually something that in computation and in communication is something that is very well studied, mainly in the classical setting, right? Because we have been doing this for a very long time. And the canonical example is this bit flip error. If you do a computation, even on classical computer, you could have an error, and then your bit that is supposed to be 0 becomes 1. And this happens with probability, like let's say p. It's actually something that happens in your laptop, in your GPU or whatever. It's just that it's let's say easy to characterize. The probability is very low in hardware, in classical hardware, and we also have very efficient way of like fixing this. It's also something that like this simple model cannot describe all quantum errors, but I will actually touch upon this. Like some of the errors we encounter in quantum computing do fit in this model, and that's the case of like readout errors, for example, which happen at the end of the secret. For genuine quantum noise, we need another formalism, and this is something that is usually called quantum noise channels. There are multiple ways actually of formalizing this. So once again, I will not enter in the nitty-gritty details. Here is what we call the Krauss representation of a noise channel, where basically you have a quantum state here with a density matrix rho, and this quantum state is coupled to an environment, which is the thing that will inject the noise. And when you try to do an operation, you will get something that is not quite exactly what you want. So this is the action of the quantum noise on the quantum channel on your quantum state. And these operators that act on your quantum state are called Krauss operators, and you can use them to understand what happens to your quantum state. So to make this a bit more practical, I've written out some example using, once again, different. So this is still the same formalism, it's just different way of writing it. So the first one with the bit flip errors, right, analog to the classical case, where with some probability p, you will actually have a bit flip, so x operation applied to your quantum state. One channel which is usually a bit more realistic is this amplitude damping channel. So you could see that in a sense it's close to the bit flip, because it's also an off diagonal. It will flip the bit, but it will only flip it if it's in the one state. So if you have a one state, you will have some probability to go back to zero. The zero state in itself is not affected. It's important to note that these cross operators are actually not unitary, right? So it's what we call a CPTP map, completely positive trace preserving maps. And this is important later on when we try to manipulate this noise. But okay, this is a very physical noise because one state are usually excited state in physical hardware. So they tend to relax to the ground state, which is a zero state. So this is actually something that we see a lot in real hardware. And then we have depolarization noise, which is a general noise that tends to take your quantum state and take it to the maximally mixed state, which is the identity here. Also like dephasing noise, which is actually the equivalent of the bit flip, but for phase flip. So once again, you can actually rewrite this like extracting E0 and E1. They would be exactly the same, but with a Z operator, just like trying to show you can write them in different forms. So these are like the main, let's say, source of noise that people consider, at least analytically. In practice, when you go down to the hardware, you get a lot of other physical quantities like T1 or T2 times, which usual square rounds of your qubits. You have like leakage and like all these other names usually can be reframed in this framework of cross operators. They will just take different forms. So it really is hardware dependent. So one important thing is to actually quantify and characterize the noise you are actually dealing with. And this, in general, if you want a full knowledge of the noise, is actually a hard task. And it actually requires an exponential number of parameters, just because you have a impulse space that is in exponential size. And tomography techniques, which are actually, the goal is to fully characterize the noise. So there are different sorts, like state tomography, process tomography, or gate state tomography. Can give you these very detailed pictures, but they are not practical at large scale. So you can do it for 1, 2 qubits. State tomography maybe for like 10, but you can't really characterize the 150 qubits device that you just got. So for this, we have other sort of technique that give you different type of pictures. First one, as I mentioned, the readout errors are actually classical or can be described by a classical channel. So they are actually easy to characterize. In a sense, you can just measure what happens if I know I have a state which should be 1 and I measure it, then I will with some probability actually measure 1, which is what I want. But because I have some readout errors, I will also sometimes measure 0 while I know my state should be 1. Do the same thing with you prepare a 0 state, which is very often doing nothing. You measure, you get a certain probability of measuring 0 knowing you prepared 0, but you also get the probability of measuring 1 knowing you prepared 0. So this is a very simple characterization, and even then, if you actually consider that measuring qubit 0 can affect any other qubit, you will still need an exponential number of circuits just to fully characterize this 16 by 16 matrix. You would need like 16 qubits, 16 circuits. Sorry. So people, even already at this stage, assume that, okay, measurement on one qubit should not affect the other qubits. So I will just factorize this matrix in 2x2 blocks. So you can actually measure all the 2x2 blocks with only 2 circuits individually. And this gives you an efficient way of characterizing without errors in this case, which we'll see we can use later on for error mitigation. So this was like classical, let's say, channel. If you want to look at quantum channels, the technique that people usually use is called randomized benchmarking, and there are actually tons of variation of randomized benchmarking. The basic idea is if you prepare a circuit, which is called like C in this case, which you know you can invert easily. So this circuit is actually based off what we call Clifford gates, because we can easily compute inverse of like Clifford circuits. So what you will see is you will implement a Clifford circuit, and then it's inverse. So you expect the state to return to the 0 state, and you measure it. And then you just make the circuit deeper and deeper, right? So then I have like 3 Clifford circuits, sub-circuits that I can invert and measure, and so on and so forth. And doing this, okay. So last variation, you can also do this interleaved version if you want to measure the error of like a specific gate. You can add these specific gates like in between this Clifford subcircuit to target a specific contribution of a given gate. But what you will do in any case is you actually measure the probability of measuring 0 at the end of all these circuits as a function of the number of subcircuits that you used. And this will decrease, of course, because you have noise. And this exponential decrease is actually directly related to the average error per gate that your circuit creates. So this is a global picture, right? It's here an average over like all type of gates. Actually, this is the formula for a gate-independent, time-independent noise, which is what people usually assume. And just a remark on the orange line here. So this is actually this is an example from the Qiskit tutorial on randomized benchmarking. The orange gate is for a particular CNOT gate that you can do between these 2 qubits. And the CNOT gate is actually more noisy than the 1 qubit gate, right? So the average error is like in blue, it's larger than the error for this particular CNOT gate. So you can still specialize with this interleaved benchmarking technique, but in general, you get a large-scale view of the errors in your circuit. Still, this is pretty useful just to compare different devices, different architectures, or different like subset of qubits if you want to know where like which qubit to use to run your circuits. And this will actually, this type of technique we will see can actually be used to get more information out of the noise model. So as I mentioned, general characterization of noise is a difficult task, and it's like exponentially hard to like represent exactly this noise. But if you make some assumption, usually based on physics, right, on what happens in your device, you can get a reduced model that captures most of the features of the noise, using wavelengths, and in this case, like a linear amount of resources. So one of the very popular way of doing so is to use what is called like this Pauli-Lindblad noise model. So as I mentioned, there are different ways of representing a noise model. So this is what goes a Lindblad master equation, which is like sort of a continuous version of the Krauss operator I described before. So the important thing here is that your noise channel is now only described in terms of Pauli operators, right? So these operators you can easily write out. And the actual noise channel associated with that is just, okay, this formula here. But what is important is you have like some identity part and some Pauli operator here with a prefactor that depends on the error rate, which is this lambda. So if you make this assumption, so this is right, assuming you can write out the noise in the Pauli basis, which is in general true. Actually, if you take all the Pauli operators, say from a complete basis, so you can do this. But what you will do then is assume that the number of Pauli operators I need is actually way lower than the exponential 4 to the n operator I would expect. And this is usually done by saying, okay, I know my qubit should only interact with the neighbor qubits. So in a sense, I have a finite range of the interaction. So I will limit all my Paulis to only weight 2 Paulis. And this means that instead of like 4 to the n, you get way lower number of Pauli operators, and you can now hope and actually do characterize all these error rates individually efficiently. So this is what is actually done, and so this is actually, if you have some time, we'll recommend looking at the paper. But there is a way of characterizing. If you limit yourself at this for this way two Pauli operators, you can actually characterize them all the error rates with only 9 circuits. So it's like very efficient, and this is done. So this is a description of how to do it. So you consider like some gates. So you want to do what is the noise associated with like this set of gates. And you will use two important techniques, which is Pauli trailing, which I will mention a bit more just after. So this Pauli trailing is actually a technique that ensures that you have a Pauli noise. So you know that right now this noise channel lambda is in the form of Pauli operators, and then I will actually measure this Pauli noise in different bases. So these are the B gates. So I will create a state in some basis. Apply my gates and measure the state in this basis. And doing so, I can actually measure exactly this exponential decay rate. So this is actually a form of randomized benchmarking or like interleaved benchmarking, because I have like these gates, which I want to focus on. I will just insert particular 1-qubit gates, which are like these Pauli trailing gates in different bases, so that I can actually get this exponential decay, fit it, and obtain exactly these error rates that I need to construct my model, right? And because these Pauli operators commute, and because they're like only weight 2, blah, 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 I only need 9 circuits to characterize all of them. So what you get at the end is actually a very nice picture of what errors do I have when I want to execute these two CNOT gates. So this particular plot is for the example A, where I have like two CNOTs. And you can see I have a lot of, let's say, Z error on qubit 1. So this is like 1467, I think is the numbering here. But I have a lot of Z error on qubit 1. I like very low error between qubit 4 and 7, which is normal because they don't, there is no gate between them. But then, okay, the 2-qubit, the weight 2 Pauli channels are actually, in this XY basis. So this is actually quite annoying because you will have like this XX rotation, which are very non-trivial, and so on and so forth. Now you have a actual description that you can look at of the noise channels that your system is subject to when you do this particular set of operation. And this only took 9 circuits once again, so it's a constant time, let's say, characterization of the noise. So, okay, now we have very nice description of noise. We know approximately what's going on. So we want to try to find techniques to fight the noise and then reduce its effect on the final results. And there are like many ways of doing this. Some of them are actually independent of the noise channel. So I will start by them. They're usually called noise suppression because they are not like actively correcting mitigating the errors. Like correcting is another word that is that has some meaning. And then once again, it's like continuous slides, all right? So I will go more and more toward techniques that requires knowledge of noise and are more specific. Okay, the first technique is actually without error mitigation because it's the simplest one, probably. So as I mentioned, the without errors are actually described by a classical channel, a classical error channel. So I will just as a repeat, if you measure some probability, you know that this comes from the ideal probability that you should expect, multiplied by some confusion matrix, which actually represents these errors, like measuring 1 when I expect 0 and this kind of things. We saw we can actually characterize this confusion matrix. So main idea is to simply just invert this matrix and apply it to the vector of probability that we got, and this should give us, the ideal probability without error. Once again, this matrix is actually exponentially large, right? So it's inverting it for like large number of qubits is actually very difficult. Even if you use this like block diagonal version, it can still be very annoying to do so. So what people do in practice in general is like this truncation trick. The main idea on this is actually to say, if my bit string was very probable to start with, then even with noise, I should still be able to observe it some amount of time. So this is exactly like in green, you have the ideal probability distribution. So if I have a bit string which has very high probability, then even with noise, probability can decrease, but I should still observe it at least once. Okay. Then because of noise, I will also have like these bit strings that should not be here, but okay, because of this random bit flip at readout, they will appear. But what I get in the end is actually a matrix where I only observed some rows and some columns. So I don't actually need to invert the full matrix to try to reconstruct the true probability. I will only consider like this small reduced matrix composed only of the rows and columns, or like intersection of rows and columns, which have the bit string that I have observed, right? Which means that if I have a small probability bit string that disappear, I will not be able to find it again, simply because it will not be in my reduced confusion matrix. But all the high probability bit strings state will be here, and so I can invert it and actually correct back to the true ideal probability in this case. Okay, so this is just a trick to go from like this exponentially large space to a matrix which is at most the number of shots you took, right? Because the worst thing that can happen is you get one bit string difference every time. And so this is something I can actually control because you choose how many shots you actually take. Another comment is actually without error mitigation is not that difficult. It's like one of the most common techniques used. But the average without error on current quantum processors like of order 1%. So it's actually a very common thing because you will usually take more than 100 samples, right? So it's something that is not difficult to implement. You still need to characterize without noise and like this, but this can be done efficiently, but has a large impact on the final results that you get. The second technique is actually, as mentioned, a lot of a very nice way of looking at noise is through these Pauli channels, right? If you can write them in terms of like Pauli operators, you can actually analytically do a lot of things. You can prove a lot of things, and a lot of techniques, error mitigation techniques, are based on the assumption that you have a Pauli noise. So how do you make sure that you have a Pauli noise? And actually, there is a way of doing this which is called Pauli trailing, which is basically saying that if I have an error channel written in terms of these cross operators, I can always rewrite it in terms of these Pauli operators, and I can also make sure that I can do this also physically on the device. So this is done by, so it's actually the same plot as before, introducing this 1-qubit gate P and P prime, which are Pauli 1-qubit Pauli operators. And P prime is just the conjugation of these Pauli operators by this CNOT gate here. So because Pauli operators and CNOT gates are Cliffords, you can easily compute what P prime should be to invert P after applying the CNOT. So what does P maps to when you apply the CNOT? Sorry. So if you do this and you randomized over all the possible choice for P1, P2, P3, and P4, you will ensure that your noise channel lambda is actually exactly of this form with some parameters that you don't know because they actually correspond to the parameters that appears in your original cross operator. But at least it is exactly written in terms of a sum of Pauli operators. And so this in itself is not a error mitigation technique most of the time because it's just a transformation of the noise, right? It's just rewriting it. Yes, sorry. Yes.
Noise as a matrix of operations like a lambda. Like, is this noise coming from the gate, or is it like something we add for mitigation or something?
So in
lambda one gate, like the noise of the gate.
So in this case, it is a noise associated to these like qubit gates, right? There is also general noise, which is like continuous in time. At any moment of time, your qubit still feels some noise, and this actually isn't harder to fight. Like the next technique, which I will present, is actually what happens when nothing happens, right? And how do you make sure that your qubit stays as it should? This technique is really when you apply an operation. So in practice, you have a lot of laser pulse if you have like some trap line of like this, and this usually are not perfect. And the main actually use of this polytraining is if my laser pulse, let's say, is not perfect, instead of doing a pi/2 rotation, I will do pi/2 plus something. And this is a coherent error, and it's actually very bad because it accumulates over time, right, in the circuit. So if I do polytraining, I will make sure that I rewrite this coherent error as a stochastic sum of the Pauli operators. And in this sense, the noise becomes random. And the nice thing with random things is they tend to cancel out. So it sends this coherent error, even if you, in itself, you don't fix the error, you just make sure that on the long run, it does not accumulate as much. This is specifically targeted towards this operation, noise associated with particular operation.
When we, sorry,
No.
so when we, this is a noise that we characterize by depolarizing channel, right? At the beginning when you mentioned the noise channel.
So in this case, noise can be any noise channel. But what you know is after training, it will be as a sum of Paulis, which is, for example, for 1 qubit, the depolarizing channel.
That's right. And like I've heard, and I also, like you mentioned, like depolarizing channel, right? And for me, it's like after some time, feel like I'm losing all the information I had at the beginning on the state.
Yes.
So it's also, I guess, connected. Like I know there's theory that using lots of data is bad, and I have, and I guess because of, is this all explained or connected to what we're saying now?
Yeah. So in a sense, whatever effect the noise had here before training will be the same after training, because this is just a rewriting of the noise in a sense. But by doing this physically, you also ensure that the true noise is actually of this form, right? So this is more like how to control the noise to be exactly how we want it to be. In this case, Pauli noise, because we know a lot about Pauli noise in a sense, and there's a lot of techniques that assume Pauli noise to work, right? And they will not work if you have other source of noise.
She meant like adding a bit of data to account for.
Yeah, so this I think this random 1 qubit gates to actually and then you randomize over, and in this case, like the noise channel on average will be written as a Pauli sum of Pauli operators. So you take any noise channel, right, and you add this 1 qubit gates, and just want to mention that as I say, more gates is bad in general, but the idea is 1 qubit gate have very like low noise compared to 2 qubit gates.
Like if it's too little.
No, so the idea is to do this around all the gates, all the 2 qubit gates, so that every noise channel is of this form, is of this like Pauli form. So you will not, I mean, you can of course do it classically, but and actually the nice thing is if you have other 1 qubit gate, you can really just merge them, and it actually does not have a lot of gate overhead. Most of the time it's 0, like the number of extra gates you need. But this makes sure that your noise channel is not of this Pauli form, right? And for example, in the previous slide, like before, I had this sparse Pauli model, right? Let me come back. And if you like, they actually have these tuning gates because they want to make sure that the noise is of this form, so that when they do this interleaved benchmarking, they know exactly that what they measure is these omega parameters. So because I know the noise as this form, because I use training, now I can use my randomized benchmarking and be sure that I measure exactly this parameter, right? And now I can use this parameter for error mitigation in another technique that we'll present shortly. So I know exactly what I measured, and I know exactly what it represents, and I can have this nice description of the noise. If I had a non-noise channel, I could still measure. I can still do randomized benchmarking, but I don't know what this parameter I just measured corresponds to. I don't know which noise it is, right? So it's a way of controlling and let's say shaping the noise that we want, because we know some noise are like easier to understand than others. So this is actually as I say, polytuning in itself is not noise mitigation, but sometimes still better to have Pauli noise. Most of the time, it's better to have Pauli noise. And here I have like two examples, which is, so the first one is the one I mentioned quickly. If you have coherent errors, so these are like this over rotation or like this type of systematic errors, they usually accumulate during the circuit quadratically with the number of gates that have these coherent errors. But if you have incoherent or like random noise, so example is this random Pauli noise, because random quantities are usually somehow cancelled, the accumulation grows only linearly. So even just using trailing, you will get a reduction in the, let's say, overall amount of noise the circuit, even if at the gate level it's exactly the same noise. The other one is more like a theoretical aspect. I think there was a lecture on variational algorithm yesterday, if I read the program correctly. One of the very nice things with variational algorithm is there is some work that tells us that, oh, even if you have noise, you should still find the optimal parameters, which is nice because then if you run this thing on something that doesn't have noise, then okay, it still gets the right answer. This is actually only true if you have random noise. And in particular Pauli noise. So in a sense, using this during a variational algorithm, make sure that you are in this parameter resilience regime where you can train even with noise, you will get the right parameters and get the right answer. And the last one is actually just you can use this trailing step on the measurement process itself to improve the computation of expectation values, because it will symmetrize the readout errors into like this matrix becomes symmetric, which is not obviously the case before. But
so the noise will not be a problem using this method because the noise will cancel themselves sometime, right?
The noise is still a problem. Like, okay, for one particular gate, whether you use trailing or not does not change anything. The amount of noise stays the same, right? So if you can say like the sum of all the coefficients in these cross operators and the sum of all these coefficients, the norm should be the same at some point and like this. The amount of noise does not change. It's just that if you randomly do movement around a given point, and then later on you once again do random movement around a given point, you have some chance that this movement cancel, right? On average. While if you have a systematic error, you will always accumulate the error, like the more gates you do. So this is just, if you have a very deep circuit, you will have less accumulation of noise, and in particular, it will not be biased. But like the noise itself will still be there, right? It's just, yeah. It's really a statistical versus like local point of view in a sense.
Average effect.
Sorry?
Like kind of need like I don't know how to say lower bound, like if it's too small or too short, if we will not get this average effect to the can, right?
Yes. This is actually it's also why it's written this way. It's not a direct relation. It's a scaling argument in a sense, right? If you have very deep circuit, then you will have the leading term will be of order L squared, and in those cases, the leading term in terms of noise will be of order L. But it doesn't tell you about the factor or like all this type of things. So it's a scaling argument in the general sense. Yes, so this is actually one thing that is important is you want to randomize over all this Pauli operation, right? All this 1-qubit Pauli operation, but you still have many of them, right? And you actually have exponentially many of them. But in practice, people have shown that a few trailing instances, so you don't need to randomize over all the possibilities for like all these Pauli operators. Like few of them tends to work well enough to get the noise that is close to Pauli in general. The next technique is actually, so it's called dynamical decoupling, and it's actually a very subtle technique, but it addresses the question you had, which is when you do nothing, you actually still have noise, which is another problem in quantum system, because then you don't really know what to do with that. So the main idea is if you have an idling qubit, so a qubit like nothing is acting on it, you can still consider that it is coupled to a bath. So this is like the system bath Hamiltonian. And this coupling, in this case, also takes the form of some Pauli operators. And so if you wait some amount of time, what is actually happening, you have a time evolution operator, which is given by this system bath coupling. And you can represent this like pictorially. So this is a representation of what's going on as your qubit is in some state, but then you have this random. Okay, it's actually not random, but you have this idling movement along like some of these directions, depending on like this coupling Hamiltonian that is there. The main idea of dynamical decoupling is to say, even when I do nothing, I will actually do something to make sure that my qubit is not going anywhere on the block sphere. And the main case for which this is used is for this dephasing noise. So this Z error that happens, mainly because it's easier to represent, but you can then expand this to general noise. So let's say I have my plus state, or like my plus I state in this case here, and I have this dephasing noise. So when I do nothing, my qubit will actually, my state will start to rotate around the Z-axis, right? So this is this yellow or blue, because don't know exactly which sign the coupling has. So you don't exactly get your plus I state, which is a problem if you wanted to have some quantum memory or something like this. What you will actually do is you will perform an operation, it's called a pi pulse, to do a rotation around this y-axis, in this case, so that you actually invert the blue and yellow points in this case. And then you wait again some amount of time. And because the same error still accumulates, you actually go back to your original point. So the idea is I have a dephasing that is a drift along the around the z-axis, right? But then if I start on the other side of the y-axis, this drift will bring me back to the original point. It is called dynamical because you need to act, right? You need to do some operation to make sure that this happens. And it's decoupling because it decouples the system from the bath, because the original and the final state are actually the same, right? So this is why it's called dynamical decoupling. This is an example for this dephasing noise. You cannot really represent it for like general noise, but you can at least write it out, which is sort of what you want. And so there is this actually a universal decoupling sequence. So let me explain here what's going on. So as I mentioned, this F operator is idling the qubit for a time tau, right? So this is a like idling window. Now imagine if I actually perform this exact sequence. So I divide my total idling window in 4, and I will perform like in between these times some Z and X operations. Okay. If you do this, so you have like a Z operation, then you wait, then you do X operation, then you wait, you do a Z operation, you wait, X operation, and then you wait. Then at the end, you know that you will actually get exactly your original state back up to some error, which is in this case tau square, mainly because you can factorize out the system part of the equation. So this is demonstrating this is actually not trivial, at least for me, but it's actually like the basis for all these dynamical decoupling sequences. You have like many of them because depending on which noise you have, you can find more efficient one. So this one is universal because it does not really care about what the exact system bath coupling is, but it also has some error which goes as tau square, tau being the time you wait, like the idling time. You have more efficient ones. Okay. In general, what is important to know is we know we can write out the sequence, right? Multiple of them have been, let's say, cataloged. You can write, we know there exists a sequence that decouple at all orders in time, but this sequence has exponentially many operations that you need to apply. So you need to divide your idling window in like exponentially like smaller windows and act with all these operations in between. So it's not a practical window, but we know it exists. And in practice, we use really these like 4 pulse or like 2 pulses dynamical decoupling sequences because they're like practical and they fit into the like normal idling time that we do. So this is an example for a very simple 3-qubit GHZ circuit. So you have the normal CZ, like C0 stair here with like the purple and the blue gates. The blue gates are like the 2-qubit CZ gates. And when you do like this qubit, actually nothing is happening to him. So if you wait, you will actually have this drift because it's in superposition. So it will not start at plus I, it will be at plus, but it will still drift, right? So what you will do is you will have actually wait some time, act with some operation, in this case the X operation, wait some time, X operation, and wait some time. So it's not this exact sequence. This is called like the XX sequence, or maybe X plus X minus. That's exactly sure. But the idea is at the end, you hope that when you arrive at the end of the idling window, you get back your original plus state. It's not exactly plus, it's entangled, but you get back your original state. One thing that is important to mention, coming back to this, you cannot add as many operations as you want because operations themselves have some time. So you cannot make this idling time window too small because then you don't have the space to make all the operations. So it's actually a very tricky, intricate technique. You need to really understand the hardware and how it works to make sure that you design good sequences that works for the particular noise you have and in the idling window that the time that you have to implement them.
Engineer, how to choose the time to apply the XA in this case?
So the main thing is, as I said, we know of sequences that are generally good, right? So this is one example. This is actually another one. I think this is probably the Qiskit default one, the X plus X minus. And because, okay, for this specific example, because this is given by, in the Qiskit IBM runtime option, people at IBM have, thought about what should be the time of this pulse, what should be this idling window, because they know the time of operations, they have all this information. So in general, it's easier if you have a very deep knowledge of the hardware. You can still craft or like engineer theoretical sequences. Actually, still a very active field of research, dynamical decoupling in general. But it's bridging the gap between the theoretical writing out the sequence and actually implementing it as a pulse series of pulse and idling windows is a big gap. That's and the latest part is usually done by hardware provider themselves. Yes, especially because this is an example. But if you look at trapped ion device, they have a very different type of noise, a specific noise that you can decouple also quite easily. But I think it's a different sequence. Actually, I would have to check. But yeah, so this is when nothing happens, you can still actually still have some noise, and you can actually still decouple the system from the environment to make sure that this is not too bad.
Do you mean that any type of hardware will have some type of problem, like?
Any current hardware will have a problem. Yes, that's. But yes, yes.
Okay. They will handle, in similar way, but different kind of pose.
Yeah, exactly, because different architecture actually have like some noise channels that are like more important and some that are less.
Okay.
So what I try to present are like general techniques. So for example, the previous one without errors is a general thing that all architectures have. Polytuning is interesting because whatever hardware you have, you will have poly noise, right? So it's a way of, let's say, averaging over like all these specific things that you might not know. And dynamical decoupling is actually very important because idling noise is a big problem in general. So now so these were like more like passive techniques, right? We did not really use any information about the noise to implement them. So by training, the goal is actually to know less about the noise and use training to make sure that it's what we want it to be. Dynamical decoupling is use information from the noise, but it's also universal in a sense. Here, actually presenting a active error mitigation technique, so to speak, where you will actually use noisy results to get better results. So this is called like zero noise extrapolation, and the main idea is I know I will have noise in my circuit, but I also sort of know that if I have more noise, the results get worse, right? So then I can try to extrapolate back to okay, if I have more and more noise, my result like get worse and worse, but then maybe I can just, extrapolate back to, oh, what if I had zero noise? So this is actually the main idea where you want to measure some expectation value, right? And you measure it with some noise factor, usually just running the circuits. And then you measure it with more noise, which is a bit counterintuitive. You get the second value, but then you say, oh, but then if I extrapolate back, if I have no noise, I should get this noise-free expectation value, right? So this is extrapolating to the zero noise limit.
What do you mean if we want to have more noise? You want to increase the layer, right?
So there's actually multiple ways of having more noise, and they actually have a big impact on the quality of the results you get. The first one is, as I mentioned, when you want to apply operation in hardware, usually have active operations like laser field or like electromagnetic field or like this being applied. Okay, it's more or less the same, but so this is a circuit which is a set of instructions represented as pulse, right? So the actual physical pulse. What you can do is stretch this pulse. So you do the same operation, but it now takes more time. Usually these have more errors. And so in this sense, you have the same operation being done, but because the time is longer, like all these decoherence effect and so on, have more time to act, and so you have a more noisy results. So you actually have increased the noise in your system, but you still measure the same quantity, the same expectation value. And then you can extrapolate back. The other way is what is called gate folding, which is basically, if I want to apply some operation U, I can also very easily put an identity after that. But identity is also just U dagger time U. So I will apply U, then I apply the inverse of U, then I will reapply U. So now when I measure here, I measure exactly the same quantity, which is my expectation value I want, but I have like 3 times the number of noise, the amount of noise, because just my circuit is like 3 times as long. As the other way of doing this is doing this on the like gate level. So for every gate in U, I will like triple it. I mean, U dagger U, and usually use this 3 or like 5 times to have like more points. The other tricky part is actually, so this is an example for like linear interpolation. So I only need 2 points. So I only need actually, so this I need to run anyway. Then I run one extra circuit and I have this, right? So the overhead is actually not that large. But it's also actually a very bad interpolation towards the zero noise because it's like linear extrapolation. So people usually use other type of extrapolation. Most of them, like the most, let's say, successful one, empirically, at least, I don't know of any theoretical results, but these are like based on exponential decay or increase in the expectation value, in the error. And you just need a bit more circuits because you have more parameters that you need to fit your model. So usually you will use like 3 or 5 points in your for your extrapolation. Sorry, there was yes.
I've used this method, zero noise extrapolation, before, but the thing is, I've tried multiple extrapolation, and what I found is like the Richardson extrapolation is really bad because compared to exponential one, because when I do the expectation values, I'm doing some expectation values of the energy. It was the Hubbard model of 2D material, and after that is like there is some type of fluctuation. When I added the noise, it was some type of fluctuation in the main energy. So the Richardson extrapolation, it doesn't.
Yeah, so I think I personally never use the Richardson one. I don't know where it comes from. As in practice, exponential extrapolation tends to give the best results. Even though I'm not aware of like analytical derivation of this. But the choice of the extrapolation is like fit is actually quite important, yes. The other thing which actually I've put in red here is that ZNE has no guarantee that you will extrapolate to the right results. So in this case, it is a bias technique, and you cannot guarantee that the bias will be 0. So there is no theoretical guarantee of convergence towards the noise-free expectation value. So yeah, it is, but it's also a technique that has low overhead. So usually people like to use it just because it's easy way to get better results. But you don't know if these results, if you could do it, infinite amount of time, you have no guarantee that you will get the exact results. So it's a more like a heuristic empirical technique than a proven one with convergence guarantee. The next one is actually very related to, it actually comes from the same paper, but really related to the noise model, poly-Lindblad noise model I presented before. So the main idea in this case is, okay, I have some operations, and these operations have a noise channel associated with them. What if I can just put a new operation that is exactly the inverse of the noise channel, right? Then if I run this, all the noise channel cancel, and I have a perfect results. This is in general not possible, simply because these noise channels are not unitary, so you cannot invert it and apply them directly. But they are like CPTP map, and you can actually use what is called like this quasi-probabilistic sampling. So as I mentioned, we describe our noise channel as the sum of Pauli operators. And Pauli operators themselves are like unitary, and you can invert them and implement them, right? So what you will do is you will, with some probability, which depends on the rate of the error channel you're considering, apply the Pauli operator, the inverse of the Pauli operator, excuse me, so that it will cancel on average the noise channel that is in front of it, right? And so you do this, and you do this for every noise channel in your circuits. So you run actually a bunch of circuits, and at the end you recompose your results by just weighting the noisy expectation value with some prefactor that depends on error rates of the Pauli operators you injected into your circuit. So this is a technique that on average give you a good expectation value. This one actually has convergence guarantee. You can show that if you sample exactly all the noise channel, like all the inverse noise channels with the right rate, and you have enough samples and so on and so forth, you will get the ideal expectation value. The main problem with that is that, as always, this actually takes an exponential amount of time. So the overhead that you have to recover the ideal expectation value is given by this parameter, which is just the sum of the coefficient on front of the Pauli operators, right? The Pauli noise channel. So it also gives you a very nice intuition, which is if you have a lot of noise, if the strength of the noise is large, then you actually have a very large overhead. But if the strength of the noise becomes smaller, then of course, like your overhead to cancel the noise is lower, right? So this is, in a sense, a very intuitive technique because we just inverse the noise. There is this tricky part with, no, it's not literary. We need to do this quasi-probabilistic sampling. But in the end, we sum everything together with the right prefactors, and we actually recover the ideal expectation value.
The question is, if we have very deep circuit, and this method gonna be very cumbersome, right?
Yes. Yes. Yeah, so it's actually the exponential, the overhead, this is for one noise channel. So the overhead is exponential in the strength of noise for one noise channel, but then you have different noise channel you need to recombine. And most of them, okay, you can actually sample these, all these inverse noise channel independently. But yeah, it is in general a very heavy technique, but it has performance guarantee. So that's why people use it.
Yeah. So the formula is taken in the account on the noise in the overall circuit, right?
Yeah, so for this, as you say, you need to know what is a noise channel because you need to invert it. So what people usually do is they use sparse Pauli Lindblad models that I presented before to characterize the noise, get a sparse, but get a noise model, and then they use this noise model they measured to invert the noise and do this probabilistic error cancellation. Okay. So this is why actually this technique and the sparse Pauli Lindblad model were introduced in the same paper, actually used in the same paper to show that it works. Because the sparse assumption is actually a good assumption, at least for superconducting qubits. Okay, this one I can maybe go a bit quicker. I wanted to show this because this is actually not a technique that a lot of people use in practice. Not this one. Especially because it's like somewhat new, but the idea of this technique is, I think, very nice and important and used in other tools. So this is why I wanted to use this one, which is easy to explain. But I think spend a bit more time than I planned. So I will still quickly mention. So this is Pauli noise absorption. So once again, it's based on the assumption of Pauli noise. So once again, this is why we usually use trailing because it's like way easier to work with Pauli noise. And the main idea is, as I mentioned multiple times, if you have a Clifford Gates and you have a Pauli operator, you can easily classically compute what is the effect of like propagating this Pauli operator through your Clifford gates, just using the group structure of the Clifford operation. And there is actually a whole classical simulation tool based on this technique, which is this Pauli propagation, which is actually exactly what it does exactly this. It propagates Pauli operator through your circuit. But people are now starting to say, okay, if I have a Pauli noise model, so once again, this sparse Pauli Lindblad noise model, I know that all my noise channels are like Pauli, right? But my inverse noise channel is also Pauli, because I have characterized my noise channel. So I can propagate my inverse Pauli noise channel through my circuit, and at the end I can group all of this here. So this is actually my normal circuit. This is my noisy operations, right, that I apply on my qubits. And then I measure some observable, which is not exactly the same as my observable originally, but is actually the corrected observable that if I had inverted all the noise channel. So you change the observable you measure to, in a sense, take into account what the effect of noise should have been. And you computed this effect by doing this Pauli propagation through your circuit. So it's a very nice idea of how to manipulate these noise channels, and actually other techniques use the same type of idea. One of them called like tensor error mitigation, which does not use Pauli propagation, but tensor network to do this. So it's a like general idea of manipulating this noise channel, like commuting and computing what their effect is at different points in the circuit. Just mention quickly that this Pauli propagation only works when you have Clifford circuits. When you have non-Clifford gates, the classical cost grows exponentially. So of course it's still a exponential cost in for mitigation. In this case, depending on the number of non-Clifford operations. For post-processing methods, so this is actually something now that happens after you run your circuit, you get your results, and sometime you sort of you know what to expect, right? Because you don't run random algorithms. That's most of the time. And there is actually two ways of, or multiple, but I represent two ways of using this knowledge, a priori knowledge, to actually improve your results. So the first one is actually close to what was mentioned before, but if you have a physical system that you want to simulate, so a quantum Hamiltonian that you want to evolve in time, Hamiltonians usually have symmetries. So this is a quick example with some quantum chemistry Hamiltonian where you have some electrons hopping and you have some interaction, right? And don't know how familiar you are with quantum matter or like quantum chemistry, but you have to believe me that this Hamiltonian will never change the number of particles in the system. Meaning if I start with like 3 electrons, I will always have 3 electrons, whatever, like how long I evolve my state. So what I can do in the end is, okay, if I start with a state that has 2 electrons in my example, but when I measure, I have one of them that has 3 electrons, that I can just say, this has to do with an error, so I can just remove it. I remove the sample from my list, and now I have like my my measurement outcome, which will just stay in the subspace defined by the symmetry of my Hamiltonian. So this is a general symmetry-based approach. Works really well with physical systems like physical Hamiltonian and quantum Hamiltonian. The other one is a bit more probabilistic and but also more general, which is if I have a quantum state and I'm interested in what is the probability of a given bit string x, I know that I know I can actually show once again actually just to emphasize that this proof is only works in the case of Pauli noise channel once again. So this gamma is the same gamma as before, which is exponential of the sum of the coefficients. So it's a very nice tool to work with. I know that if I measure my noisy state, I will get a noisy probability, which is bounded by the true probability and the noise factor. So I also know that if I sample square root of gamma more time, then I will have, if this is non-zero, then I will have a chance to actually observe the bit string I'm interested in. So what people have done is they say, okay, if I take all my bit strings, right, and they all have like some objective value, like some Hamiltonian or whatever, I can use this, cumulative distribution. And if I take the average, so this is the noisy expectation value that you will get, I can correct it because I know what is the noise factor. I can just only take the tail of this distribution and get a corrected expectation value, which is this dotted line, which is actually much closer to the true expectation value, which is this line dotted here. So this is just actually, once again, knowing what is noise and using this to say, I will discard the results that are not in this window according to this factor gamma here. So I will only focus on the low tail of the distribution.
This guys has been done in classical computer, right?
Yeah, this is so you sample bit strings from the quantum computers, right? So then you have a bunch of bit strings. You compute the expectation value or like the cost of all of these bit strings. So you need to have some problem, right, that you want to try to solve, but and you get this cumulative distribution, right? But you know that the probability of the good bit string is actually related. Your noisy probability of the good bit string is related to the true probability of the good bit string. So what you say is, okay, now I can actually focus on a tail. So in this case, the tail actually take only 0.01% of the full distribution. So they take only like this part to compute the expectation value. And doing so, you get a new like truncated expectation value, which is actually much closer to the real expectation value. Just because you assume that all the rest is due to noise. It also tells you that if you actually took 1,000 more samples, actually probably 10,000 more samples, you should actually get the true expectation value, but this is way more costly. So usually you just do this classically, you truncate. So yes, this is a classical post-processing technique. Once again, based on knowledge of the strength of noise and things like that.
This method is implemented in Qiskit or other languages, or we have to implement it by ourselves?
I don't know if it's so. The main thing is this is problem specific, right? Because you need to be able to define this objective value. You need to be able to compute this CFD, stuff like this. I know probably in Qiskit optimization, you should have this somewhere. But in the like pure Qiskit, I don't think so, because they don't have a lot of problem related things. That's the same thing as the symmetry based post-processing. Usually, because it's problem specific, it's not implemented. You need to, because you need knowledge of the problem to actually do it. Okay, this is maybe the last part. So we have seen like a lot of different techniques, and then the main question could be, okay, which one do I use? The answer is usually all of them would be good, but all of them is very difficult. So this is just a recap of, for each of these techniques, what do you need in the pre-processing? So, a lot of noise learning, for example, without noise learning, or like randomizing over like a lot of party operators for trailing, and this type of stuff. What do I need to run? A lot of them need extra circuits to run to actually, implement the error mitigation. So you have all this trailing stuff. Dynamical decoupling can be inserted in all the idling time and all the possible noise inverse circuit for probabilistic error cancellation. And then you need some post-processing, because you need to recombine all these extra circuits that you got, weight them correctly with different prefactors, different signs. So a lot of averaging or like extrapolation if you do ZNE. Some of them, okay, the main difficulty actually is using these techniques. Let's say it's not an abelian task. Right? If you permute some of them, you will actually get different results. This is actually very non-trivial, but an example could be if you do probabilistic error cancellation, right? So I want to implement this inverse noise channel in my circuits. I also want to do polytrailing. Should I twirl my 2-qubit gates before or after I implement my inverse noise channel? I think in this case, actually, it doesn't matter in this example, but this is the type of question that you should ask and keep track. So it's a very difficult task. So in general, the error suppression technique can be used quite freely. It's dynamical decoupling and polytrailing. And without error mitigation should be used also because it's a low overhead, easy to implement technique. Like then for like ZNE, probabilistic error cancellation, because this is a technique I didn't present, but like this renormalization technique, you cannot use them always together and like this, so you should be more careful. And actually one of the big part of what we do at Haiku is actually building this error mitigation stack, so which is not just a technique, but implement all of this technique in an optimized fashion. And this is, let's say, some advertisement. So this is utility experiment that was done by IBM in 2023, I think, was they studied the Qiskit model on 120 qubits on their hardware. And they use actually probabilistic error cancellation without error mitigation and dynamic decoupling. And the estimation is actually it took them few hours of quantum runtime, right? So time spent on quantum computers. We actually reproduced this experiment actually not using probabilistic error cancellation, but using a combination of a lot of other error mitigation. We got very similar results, but this time it actually only took us seconds, a few seconds of, I think it's like 15 seconds of quantum runtime. All of this because, okay, first of all, probabilistic error cancellation is a very heavy technique with a lot of overhead. And the second one is actually, with all these noise learning steps and number of circuits you need to create and reassemble, you can easily do it inefficiently, right? And so if you do it in a clever way, you can really reduce the number of extra circuits, batch them efficiently together, and submit them in a let's say more favorable way to the cloud service in this case.
You do not use the same method, but you get the same results.
In this case, yes. So I mean, in this case, we did not use error cancellation, for example, probabilistic error cancellation, yes. Mainly because our goal was to have a low overhead. And also, so this is just more on the classical side. As I said, you need to keep track of all these different circuits to combine them efficiently and so on and so forth. So this is just a classical, this time, runtime you need for this experiment. If you do it with normal Qiskit tools, or if you use our own orchestration of all the error mitigation here. And okay, it's like 15 times less. So this for one circuit is not important, but if you do variational quantum machine learning or variational technique, then classical time also becomes a problem. I had planned a quick part on error mitigation for logical qubits, but I think we are no problem.
Yeah.
Okay. It is actually a tentative session that I added, let's say at the last minute, because
we planned for the delay already because the talk after that's arranged between us.
Okay, perfect. So yeah, it will not be in detail, but it's just getting some ideas of what is to come, also in the midterm, let's say. So as I mentioned at the beginning, a lot of the other providers now have logical error correction coming up in a few years to let's say 2 to 20 to be to be large. But there is actually a lot of people, us included, thinking that the transition between what you have now, like this noisy intermediate scale quantum computers, and the fully fault tolerant quantum computing will not be a sharp transition. And in a sense, it will be a gradual improvement that will include error correction at first with small distance codes and like this. And we think that in this transition regime, error mitigation will actually still be very relevant. And I have a few examples to stress this. So this is actually a paper that was one of the first to try to define exactly how important it will be. So they introduced this scalability variable, which actually means if you have a quantum computers and you have 100 qubits, you're very happy. You know that if you want to do error correction, you need way more of the order 1,000. And the problem is when you go from 100 to 1,000, it's very, very hard to keep the same error rate. Scaling up the size of the quantum computers while keeping the error low is very difficult because you have all these crosstalk that happens. You have the size of your chip is larger, so you need to pull it down, maybe differently. So it's hard to scale up while keeping the error rate low. And this, let's say, ability of doing this is this scalability parameter that they introduced here. And the color map here actually is the number of physical qubits you need to implement a, I don't know exactly, should be 10 logical qubits or something like this. So it's a number of physical qubits you need depending on the scalability that you can have. So how to read this is, when I scale up, I really have no extra noise, then okay, I can just reduce the noise and I'm very easily in the good regime because I need I don't need a lot of many qubits to do the logical one. But if my scalability then becomes larger, I need more and more physical qubits, right, to actually implement the same number of logical qubits, depending on the starting error threshold. And then there is this regime where you actually don't need 100 qubits to do a logical one, but you need like 1,000 or 10,000 and 1 million and like this, right? And so this transition in this period, in this regime here, you will not be able to have 100 logical qubits just with your 10,000 because noise will become too large and you need to scale up the code and blah, 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 blah. So all of this to say, it's very hard to, at the same time, have a lot of logical qubits while being the like most efficient implementation of in terms of physical qubits. So a lot of hardware providers right now, they say, oh, look, they actually follow this line, like in what they tell you. They say, oh, we have this code. So for example, IBM has this so like private bicycle code. I think you have error correction talks coming up. So they will tell you, okay, once we have one logical qubit, then we can just scale up the physical, and it's a linear ramp, linear line, and we end up like somewhere here in like 2030 or whatever. But the truth is, when they do this, noise will increase. So what they will actually get is like this curve line, where even if they increase the number of physical qubits, very fast, the number of logical qubits they will be able to implement will be limited. So because you cannot do anything interesting with 10 qubits, the likely solution will be to reduce the code distance, so have more noise, right, but more logical qubits, and then you can add error mitigation on top of this imperfect logical qubit to actually get good results. Hopefully, utility scale results. So for this, you still need to rethink a bit error mitigation with error logical qubits. So these are actually very recent papers. I will, because these are techniques we already mentioned, I will just quickly go on what is different. So in zero noise extrapolation, you actually have a very interesting new way of scaling up the noise. So just for reminder, you want to measure the thing at different noise level to then extrapolate back to the zero noise level. But now that you have logical qubit, you can actually say, oh, but instead of using this distance 5 code, I can use this distance 7 code, and I have less noise, and I can extrapolate, and so on and so forth. The main question that remains, and it's actually what this plot is trying to communicate, I don't know if it's good for that, but we don't know yet what is the extrapolation function we should use, because we don't know what is the noise model for logical qubits. And so it's really unclear how we should extrapolate these noise scaling results to the zero noise case. So yeah, this is an ongoing, let's say, research. And the other one is actually dynamical decoupling, once again. When nothing happens, even logical qubits have errors. So we need to be able to correct that. And I like this, in particular, this paper, because it mentions the 2 types of dynamical decoupling you can do when you have logical qubits, which is you still want to do your physical dynamical decoupling, the one I presented before, because physical qubits are still idling for a lot of time. But then when your logical qubit is idling, you need to think about what is noise model and what is the system path interaction, so that you can devise a dynamical decoupling sequence that acts on the level of the logical qubit and decouple the error-corrected subspace from the environment. And actually, what is also cool in this paper is they have actual results. So this is not exactly error correction, but this is error detection done on IBM hardware. So quickly, you have some Bell states. So it's a 2-qubit example. And if you do nothing, of course, the fidelity drops because of idling noise. But then if you do error detection, you will actually get, which one is it? Yes, this orange curve here. So of course, it gets a bit better because you can remove the bad samples. On the other hand, if you do dynamical decoupling, you get the blue results. So once again, you still have a drop, but it's way better than doing nothing. If you combine error detection and dynamical decoupling, so this is exactly what you would do here, you would actually get a much higher fidelity for even long idling time in this case. So this is really an example of combining dynamical decoupling and error detection in this case, but the same would apply in error correction at the physical and at the logical level. Okay, a quick conclusion. Noise, okay, right now is really what makes quantum computers difficult to use and at large scale. there are a bunch of error mitigation techniques, each with their own strengths and weaknesses, and sometimes it's very difficult to pinpoint which one you should use. So it takes a lot of time. The underlying message is you usually have exponential overhead. So if you want to go back from your noisy results to your noise-free results, you will need exponentially more circuits or more classical time, or one of them. Combining error mitigation techniques becomes very complicated very fast because you have most of them create many circuits that you need to sample, and you don't know exactly how many times you should sample all these circuits, how many randomized instances, and things like this. So orchestrating like the mitigation stack and not technique individually is actually very important. It can reduce the quantum and classical times that you need. I just want to mention that you will still have a exponential scaling of the overhead, but let's say the prefactor can be much lower. Finally, this was a quick part at the end. Our mitigation will stay relevant in the near-term early fault-tolerant regime. And some tools will probably stay relevant even in the fully fault-tolerant regime. I think dynamical decoupling is a good example of this, where if your qubits are not doing anything, you might as well use dynamical decoupling.
Thank you.
And this is, once again, just
So thank you for this very nice talk. It was very clear. I think you understand, and if we have any question, we will contact you on Discord. And
yeah, I think I will be here. Yeah, I will stay around. So sure.
Like it was not presentation, thank you, but I have questions like this is really deterministic and all of this, because this methods like you can do it on your own. But what do you think like nowadays with the growth of the AI and quantum machine learning? Like, do you think like there's a way to do some error correction with this type of method?
So in a sense, this there are already a lot of tries in this direction. So for example, for the dynamical decoupling thing I presented, I mentioned you can write out this universal sequence, but you can also imagine other sequences for specific type of noise and things like this. And there are actually people using reinforcement learning to try to find this dynamical decoupling sequence that are the best for specific hardware, right? So this is something that already exists, and people have been playing around with that for some time. There are also in this more, I presented this polynoise absorption, where you commute all the noise at the end and then try to do it this way. People have been using tensor network-based method to do this instead of the poly propagation, and now they are moving toward, because tensor network are actually quite close to a neural network in a sense, so they are moving towards this neural network-based approach where I have a given circuit, I have my noise model, and try to predict what should be the final observables that you should measure to have the noise-free results or something like this. So like AI for quantum, in a sense, is already a big topic. A lot of people looking at it from this point of view. The main thing is then it's hard to get guarantees, right? Like
yeah, that's the thing. Expectation value is quite close to what we can do like methods.
Yes. The main thing is, so right now, I would say all the quantum circuits that are run, we know the answer of the circuits, right? Because no one, or like very, very few people are doing things that are not classically simulatable or checkable, right? Because we are still in a phase where we try to understand what is going on and or to use them properly. And so this means that it's not a big deal if you don't have guarantee on the results. But in the future, if you imagine, no, I have new circuits, like I cannot know the answer right in advance, and I run it, I want to be sure, or I want to have a confidence interval, or I want to estimate, or sure am I that this is a good answer, right? And in this sense, having no guarantee, like the ZNE, it's one of the big problems, which is you extrapolate, you get a better result, but what if it's not better, right? Or how far away is it from the true answer? Like all these questions become more problematic as you get towards like more difficult problems, more interesting problems. And I think for me, this AI for, I mean, this is a personal opinion, but for this whole AI for quantum type techniques, it's very hard to get this type of guarantee. And so it's very hard to then implement them with high confidence, let's say. Also because noise models are complicated, so even you come back to this dynamical decoupling example. either you train your reinforcement learning on your device, but it takes a lot of time, right? So you need to have a lot of access to compute time to do it. And even, this is idealized version, the noise on quantum computers change from one day to another and like this. So this is also another problem. Or you train it with a simulator, but then you have a simulated noise model. And how good is your simulated noise model to the true noise model is then the question. So it's, yeah. That the possible probability of cancellation is a least. It takes a lot of extra samples to get the good results and like this. But at least you know that if you increase the number of samples, you will get a better answers, right? It's a very solid method to gradually improve your results.
Any more questions? So, well, thank you, Maxence, for this presentation. That's fine. So we move on directly for a hand-on section presented by Redex from NSUT New Delhi from India. Please, Redex, join us.
Good afternoon. I hope you can hear me now.
Yes. You share
So can you hear me?
Yes, very well.
Yeah, good afternoon. It's a good afternoon in India. Yeah. So let me share my presentation first. Are you able to see that?
Yes. When you make an presentation mode, then everything is perfect. Then you can start.
Okay, just give me a second.
Yes.
I hope you can see that now.
Yes.
Okay. So first of all, my name is Rudraksh and I'm from India. I'm a data scientist and Qiskit advocate. And recently I completed my master's in physics. So I'm here to present a hands-on session in quantum error mitigation from noise to signal. So if you can see the QR code, you can contact me through the LinkedIn and email. You can find all on the scanning the QR. So let's get started. First of all, thank you for joining our event. And I hope you will learn good from this event. And so this is the overview of the session I will provide. And through this PPT, I will provide you the whole summary of the notebook. And after this presentation, I will take you to the notebook and teach you how to code and how to reduce error with the mitigation technique. So let's start with the summary. So this notebook serves as a comprehensive educational module designed to demonstrate the challenges of noise in the NISQ era and the software techniques used to mitigate them. So by guiding through a progression on ideal simulation to a noisy hardware models. So the project illustration illustrates how the quantum error mitigation can recover the accurate results from the imperfect hardware without the need for full quantum error correction. And so experimentally workflow. So first of all, the ideal baseline. What is the ideal baseline? In the ideal baseline, we will establish some ground truth with perfect simulation where there is no noise. Then we will going to simulate the reality, introducing realistic hardware noise. And after that, we will going to introduce mitigating readout error. And then in fourth, we will going to mitigate the gate noise. And in last, we going to use modern Qiskit primitives like runtime v2 for doing this all in one step. So as I said, the phase one ideal baseline, we are going to create a bell state and I hope you know the Bell states it will in the superposition of two states of 0, 0 and 1, 1, which will in the 50% of 0, 0 and 50% of 1, 1, and there is no probability of any states like 0, 1 and 1, 0. So first we will going to create this, and in the phase 2 we will going to simulate the reality, and we will going to use two fake backends here. One is fake Manila v2 and second is generic backend. This backend mimics the physical noise properties like T1, T2, and gate errors of real IBM quantum processors. Then we will transpile and execute our Bell state circuit on the noisy backend. Then we will know the impact of noise, like the output contained states like 0, 1, and 0, and discrete probabilities, demonstrating the impact of hardware noise. Phase 3 will be going to have mitigating techniques like mitigating the readout error and generated and ran circuits for all base states like 0, 0, 0, 1, 1, 0, 1, 1 to characterize measurements errors. In modeling, we will going to build a confusion matrix. We will visualize the probability of detector, which we is identifying a state, and then we will going towards the correction. The correction is like the calculating the inverse of the confusion matrix and applied it as a linear filter to the noisy Bell state counts. And in phase 4, we're going towards the mitigating gate noise through ZNE. ZNE is also known as zero noise extrapolation. And in this, we will implement the unitary folding to artificially increase the noise level of the circuit by 1x, 3x, and 5x without altering the logical cube output. Then we will do the measurement, calculate the expectation value for each noise scale. We will do extrapolation, perform the linear regression on noisy data points to extrapolate back to zero noise. Then we will get the results like the extrapolated value was a closer to ideal target. And in last, we're going to use Qiskit primitives like runtime v2. There are two types. We have sampler v2, which is going to use a configured sampler v2 for error suppression. We are dynamic decoupling, and we will going to use estimator v2, which is going to be automatically apply the ZNE. So these are the technologies we are going to use. So first of all, we are going to use Qiskit SDK. Then we are going to use Qiskit AER and fake Manila for fake provider for realistic noise and modeling. Then we will going to use primitives v2, and we will going to use mathematics like linear algebra, NumPy for the linear algebra, and we will going to use some metrics here. Then we will use matplotlib for the visualization. So this is for only for the PPT, and now I will share the screen for the notebook. Please give me some minutes to share the notebook in the Discord. Ben, can you share the notebooks in the Discord?
Not yet.
Okay, so let me do it.
Will you share it, right?
Yes, I'm sharing. Please wait a moment.
We do not see anything on screen.
Yeah, I'm not sharing the screen right now. I'm sharing the link in the Discord. So can you please give me some minutes?
Hold on.
So I shared the notebook in the noise and error mitigation channel in hands-on practice section in our Discord server. So let me know if you can open it through Collab or you can download it and use it on the VS Code.
Is your notebook on the GitHub repository? Correct?
Yes, I uploaded the notebook on the GitHub repository.
So share the GitHub link.
Okay.
You have GitHub link? And you can connect to.
I tried to do the edit.
There.
Yeah, I shared the GitHub link and you can find the quantum error mitigation file in that. Let me share in the chat as well.
Just your email.
So I hope you guys can find the link. Let me know in the chat. And you can open it on like VS Code and you can open it on Google Colab also.
Do you have the link? GitHub?
Okay.
Yeah. How about you?
Yeah.
Everything is good.
So can you open it on so should I start?
Just 1 minute, a few minutes more, please.
Okay, no problem.
Yes. Okay. I think you can start. People online is okay.
So if you all guys can open it, then let me know in the chat. And if anyone has the issue, let me know in the chat as well.
Yes. So it's easier if
So
you question in Discord, and then if we are not able to answer for now, we can answer later. But we try.
yeah, so after I will cover the all questions after this session. Don't worry. And let's get started. First of all, welcome to the Qiskit Fall Fest. And in today's session, we are going to understand and mitigating the quantum noise. So first of all, why we need error mitigation and what is the noise and what is the challenge in quantum computing in today's NISQ era and how we should tackle this. We are going to cover in this notebook with this some real codes. So for this, we are using two fake backends. One is generic backend V2 and one is fake Manila. You can use both or you can use one as you wish. So first of all, we are going to uh, do some imports. And if you are using this first time, and if you didn't use Qiskit before, you have to install modules. So you can run this code, then you can know what modules you are lacking, then you can install through pip PyTest package installer. Then let's start it with the section 1. What is the ideal quantum world look like? So I'm assuming that you know the basics of quantum mechanics, linear algebra, mathematics, and also the basic Python programming here. And also, if you have some issues, you can tell me after this session. So I hope you know what a qubit is, and uh, qubit is a basic unit of information. Unlike all classical bit, which is only 1 or 0 at a time, a qubit can be in both state, like some percents in 0 and some percents in 1 at the same time. Superposition, the ability of a qubit to be in combination of both 0 and 1 simultaneously, and how we can achieve superposition by using Qiskit. So we can apply the Hadamard gate, and Hadamard gate can be applied like this by applying the H to any qubit, and if we apply a Hadamard on 0 state, then it will convert in 50% of 1 state and 50% of 0 state. Then is the entanglement. So it's a special connection between two or more qubits. If two qubits are entangled, their state remains linked, no matter how far apart they are. So how we can apply entanglement? So we have to apply a C0 gate, which is represented by Cx, and in Qiskit we can apply it through .cx, and it is a two qubit gate in which we have one is control qubit and another is target qubit. Then we are going to use the quantum circuit, and we can have the measurement, the acting of looking at a qubit, which forces it to choose a classical state. So it's superposition, it's collapse when we measure it. It will be 1 or 0 after the measurement. We will use the AER simulator of the Qiskit. It's a classical program that pretends to be a quantum computer. So after that, we have shorts. Shorts is the number of times we run the exact same circuit and record the measurement. Then we have the counts. Counts is like how much our by strings got the measurement. Like it's the number of the measurements our states get. Like if we going to use a Bell state, which will have only 0 0 and 1 1, so then it will tell how many shots 0 0 get and how many shots 1 1 get. So let's start with the perfect experiment. So we will going to create a Bell state, and I assume you know the basics of Bell state. Bell state is only to entangle two qubits. When measured an entangled Bell state, you should only get 0 0 and 1 1 for the 5 plus Bell state, and there are other three Bell states also, phi minus, psi plus, and psi minus. And for 5 plus Bell state, you should never get 0 1 or 1 0 for the no noise simulation or real measurement. So first of all, let's start with creating our quantum circuit. And we can pass the quantum circuit in a variable. This 2 means here is we are going to have two qubits. So this will make the quantum circuit with the two qubits with label 0 for one qubit and 1 for another second qubit. Then we will going to apply Hadamard gate as I told before on the 0th qubit, and it will change their state in for the superposition. Then I'm going to apply a control node gate where has control on 0 and target is 1. Then I'm going to measure all by using measure all function. And for this, we are using a AER simulator. So I'm going to create an variable name ideal job in which I will pass the ideal simulator, which is AER simulator, and I'm going to run the Bell circuit, which is our quantum circuit, and I'm going to run it 1,000 times, and then I will going to get its result in the form of counts. Then I am going to print the counts and plotting the histogram. And as you can all see, we have the perfect counts of 0, 0, which is 500 times, and 1, 1, which is also 500 times. So this is the noiseless measurement. There is no noise here. Each states are divided into perfect 50-50%. This is the perfect histogram we can get without noise. Now let's learn about what is noise and who is our enemy. So our enemy is quantum noise. So what is a quantum noise? A noise is anything that causes our quantum system to deviate from the perfect picture. So let's take an analogy. Analogy is like you have the coin. For heads, you have 0 cat, and for tails, you have cat 1. And superposition is like spinning the coin perfectly on its edges. So we are going to have 4 types of error here: T1, T2, gate error, and readout error. In T1 relaxation error, the excited state, which is cat1 state, is not a stable state. So it will eventually losing energy and relax or decay back into a stable 0 state. The T1 time is the average time it takes for this to happen. Okay, then the second error is our T2 error, which is this error destroys superposition. It's a loss of phase information. The T2 time is the average time a qubit can stay in superposition. So it's like when you applied a Hadamard gate on a qubit, then it's the average time your qubit is going to stay in the superposition before its phase is randomized. You can read the analogy. And the third one is gate error. And gate is like an operation, like a laser pulse that is supposed to be perfect. Like if you want to rotate a qubit by perfectly 90-degree, and gate error means the operation is on float. Like you only able to get it rotated by only 89-degree or some less degree than 90% or maybe more degree than 90%. Then the less or more will be our error. Then lastly is the readout error. In the readout error, a measurement error where the detector misreports the qubit's final state. It sees a 0 but reports as a 1. So it's the measurement error when you are not measuring the qubit as it shown in the results. Then in section 3, seeing is believing. Let's simulate noise, how the noise is affecting our quantum. So as I told, we are using the fake backends like fake Manila and noise model, a Qiskit object that holds a collection of noise instructions. Then we are going to use AER simulator. Then we are going to transpile our circuit with the backend. So let's do this. So first of all, I'm going to pass the generic backend v2 as in the backend. You can use anyone if you want. If you want to use any other fake backends, there are plenty of many fake backends. You can find it on the Qiskit website. Then I'm going to use AER simulator to get the backend from this. So this pass the generic backends in the AR simulator. Now we are going to transpile our bell circuit which we created in the section 1, and we will passing through this is the simulator which is going to be our fake backend. So we are going to run this for the 1000 times, and then we are going to get the results in the form of counts. Then we are going to get the real counts. Then and after that we will plotting the histogram. And as you can see, our states are not 50-50%. We are getting some error here. As you can see, the 1 is 502 times, 0 is 487, 0 is 3 times, 10 is 8 times. But in the noiseless performance, we can see that our measurement is only 50-50% for both 0 and 1. But we can see that our 0 states and 1 states are not equally divided. We are getting some measurements in also 0 1 and 10. So this is how noise can make our measurements, and this is how the real noise can affect our uh, calculations if you are going to solve a problem. So this is the first exercise. You have to do it on, and if you got some issue with it, you can contact me later. I will check the Discord server.
It's about
Then we have the section 4, which is the mitigation one. We are going to fight the readout noise. As I explained what is the readout noise, and there are some key definitions like what are quantum error mitigation. It's a collection of software techniques that don't fix the hardware errors, but it estimates what the noise-free answer should be with mathematics.
I have it.
We are going to
You
use confusion metrics, and if we prepare 0 and measure it 90%, and we have time with the 0 1 we have measured it 10%, then we record in the matrix, then we can see through the matrix what is the error we are getting. And we are going to use inverse matrix also to multiplying our noisy results with the inverse matrix. So these are also some imports. We are going to import some matplotlib, numpy, and we are going to use fake manila this time. And we are again creating the bell state. Like we created a quantum circuit with 2 qubits known as bell. We applied Hadamard gate. We applied a control node gate with the control on 0 and target on 1. Then we are going to measure them and going to run them 1000 times. So we all did it in previous cells. So these are the labels, is the list of the states we are going to get from the bell state. So we are going to create here a matrix with the numpy. So np.0 means it will going to give you a 4x4 matrix with all zeros in it. Then we are going to apply our results into this, and then we can get this type of matrix. This is the confusion matrix. As you can see, in horizontal we got the prepared state, and vertically we got the measured state. So we prepared 0 so it will get the 98% times 0, but you can see this this time it gets 1% 0 1 and also 1% 10. So it is showing how much error we are getting. And you can also see that like 0 1 we have prepared the 0 1 state, and 96% times we got the 0 1, but 3% we got the 0 0, and 1% we got the 1 1. And This is how we can know about which state we are getting and how much error we are getting on the each states. We use scipy.linear algebra.inversion to invert the matrix. This is the basics in the Python. I hope you know the basics programming language in Python. So first of all, we are going to import our scipy.linear algebra. Then we are going to try to inverse the M matrix. And if there is error, we are going to accept that. So it didn't show any error. We are going to define a function here, which is apply mitigation, which is going to pass noisy counts, inverse matrix, and labels, which contains the list of states, all four states. Then we have noisy vector, we have mitigated vector, and then we have applied this function through noisy counts, inverse matrix, and labels. Then we printed our noisy counts, then we printed our mitigated counts. And if you can see that clearly, their noisy counts is 0, 0, 4, 1, 1 is 471, 0, 0 is 490, and this is like that. And if you can see the bar chart, then you can see our blue line is the ideal, like for 50% of both states, 0, 0 and 1, 1. And orange line is the for the error, which is the noisy. And for the green, we are getting readout mitigated. So what happened is we mitigated our readout error from this orange line, like is the noisy, we are getting the less probability. Then we took out the readout error. Then you can see our uh, probability is increasing in greater than the orange one, and in also this greater than the orange one. So that's how we can mitigate the readout error using some codes and software. So this is again is the it's the uh, exercise number 2. You have to do it on. And if you are going to have some issue, you can contact us. Then it's the section 5, mitigation number 2, fighting gate noise with the ZNE. So what is ZNE? ZNE is ZNE's full form is zero noise extrapolation. Zero noise extrapolation is a quantum error mitigation technique. It helps to estimate what the results of a quantum computation would be if there were no noise, even though you only have to access the noisy quantum hardware or simulators. So, as we saw why we need it, why we have to reduce noise to get the most probability and correct calculations. So, how does it work? We have to run our quantum circuit at normal noise. Then we artificially try to increase the noise by folding gates. Like we have to replace one control node gate with 3 control node gates in a row. So this doesn't change the logic, but it increases the noise. Then we're going to measure the results in the form of expectation volume at each noise level. So after that, we are going to fit a line to these results and extrapolate back to zero noise. And the y-intercept is our best guess for the noise-free answer. So these are the key definitions. I explained what is a gate noise. Expectation value, it's unlike the counts. Uh, it's like a physical property, measuring a physical property in a single number between -1 to +1. Then we have the unitary foldings. To understand the noise, we intentionally make it worse. We replace a single gate U with the sequence of U, U dagger, and U. Mathematically, U dagger is the inverse of U. Physically, we just ran 3 gates instead of 1. We collected the 3x noise, then extrapolation. So our ideal goal is to get the 1.0 plus 1.0, and as all I said before, we are going to use 1x, 3x, and 5x circuit depth. We are going to run them and calculate the expectation value. We are going to use linear regression to extrapolate. So this is all the imports. We are going to use fake Manila for this time also. And again, we are going to create a bell state. So after this notebook session, you are going to know what is a bell state and how to code a bell state, how to reduce error in a bell state through the code. So we are going to define a fault circuit here. So if our scale factor is 1, we will return our QC. And as you can see, a gate is instruction dot operations, Q bits, control bits. These are this is the for loop, and this is if. And then we return the folded QC, which has all the qubits and gates applied on them. So here you can see the QC1X is the fault circuit. We applied the function here with QC base is the our normal bell state, and we applied one time. In 3x we applied 3 times, and in 5x we applied it 5 times. Then we printed it, and this is the our circuit. So now we run 3 circuits, then we must convert them into counts, and then we convert them into a expectation value using this formula or this code. We are going to take a list of all the circuits, and thereby we are going to transpile all the circuits with our fake backend with optimization level 0. So then we are going to run this circuit with the 4000 times. Then we are getting the results in variable result, and we are going to store expectation values. Noise factors are 1, 3, 5. We used a for loop for it. Then we printed it, and as you can see, our expectation value for 1x is 0.8835, 0.8425, 0.8465. It should be 1 for the noiseless, but we are getting less than 1. Then we know that it has some noise. Then we are going to use linear regression here, and we have some slope, intercept. We are going to use numpy to fit our noise factors expectation value, and we uses we passed it into a variable named ZNE mitigated value. Then we are going to plot them, and this is the plot, and you can see our noisy result is 0.8835, but our ZNE mitigated result is 0.8852, and this is the mitigated result, and this gray dots are the ideal value, which have to be 1, but and this red dots is the measured data, and we mitigated it, and this star with has a y-intercept is the our Z and E. So we mitigated some error from this by using regression and simple mathematics here. So there's another exercise you have to do it on. And this is the last section of this notebook. And in this section, you are going to do it in a one go. We did it everything manually in all other sections to understand the concept, but here we are going to use the sampler and estimator to handle specific types of error management automatically. So we are going to use sampler v2 from the Qiskit primitives v2, and we use this when we want the counts. It focuses on error suppression rather than mathematical mitigation. And for the estimator v2, we use this when we want the expectation value. It uses when we mathematically want to cancel out noise, then we are going to use resilience. In sampler, we don't use resilience. We will use dynamical decoupling. For estimator, we are going to use resilience. These are the differences between the sampler V2 and estimator V2. You can read it. Then this is the automation sampler. This whole code do what we have done in all previous sections. We have created the bell state again here. We have passed the fake manila. We have say used sampler v2 with fake backend, which is the fake manila. We have the shorts, which is 2048. This has a different style to pass the number of shots. So you have to learn based on the version of your Qiskit. And this time we are going to pass dynamical decoupling for the estimator. Then we transpiled our bell circuit and fake backend. Then we run it. Then we get the results as in the variable result v2. Then we get the measurement counts. Then we plotted it. And as you can see here, this is our whole notebook in one code. The without noise, we have 0, a blue line with 0, 0 at 0.5 and 1, 1 with 0.5. But for the sampler, we do fake manila, which has the error. It is 0.51 for 00, 0.015 for 101, and for 10, it is 0.014. And so orange one is the error one, and blue one is the ideal one, which we reduce the error to get to the blue one with this whole code without using separate cells. So this is the end of our notebook, and this is the conclusion, like what you learned about from this notebook. So you learned to quantum error mitigation. What we did today, it's a set of software tricks to estimate the ideal answer from noisy results. And later, in the later term, we are going to explore what is quantum error correction, and our teammate Mona will introduce you to quantum error correction and provide you the hands-on session. So what you have learned. So in ideal world, there is a perfect quantum circuit gives a clean, correct answer. But in real world, we have some noises like for T1 noise, T2 error, gate error, and readout errors. And we ran our real noise on in this notebook. Then we learned about it, how to manually fix the how to manually fix our readout error, how to manually fix our gate error. Then we done it automatically by using sampler and estimator. So that's it from my side. Thank you all. And if you have some questions, you can share it on the Discord as well as on the in this chat. I will try to provide answers for all of your questions. Thank you all.
So thank you. We'll try to do exercise, and then if we have any question, we will contact you on Discord. Thank you.
Yep. Thank you. Thank you so much.
Can anybody run the code on your local machine? Works for you? Ui đơn vị tung.
A break?
Why don't we break?
Oh, you can take any break if you want. The most important that you learn something and then you take a break and and if you have some questions.
So it's like this timing I have to go back.
Okay.
But it's okay, right? Like tomorrow I can come.
Yeah. Yeah.
But we finish this after we were
So for the hand-on exercise, we let the other people on, and then in after there our selection.
all of this will be uploaded in
Yes, try to recall. But we hope that
whenever I can. I want.
thank you. Don't worry.
Oui, vamos de nuevo.